So one thing I want to talk about is that here it is possible for a maximum or minimum value in a linear programming problem to occur at two different vertices. So for example, the vertices of the figure shown, this figure down here, 7.27, notice that when we plug in the values, we get a maximum value of z at 2, 4, and also at 5, 1. So we're getting the max values here at 2, 4, and at 5, 1. So again, that's why it's important to plug in the values. And so in that case, and you'll see this in the homework, in this case, the objective function has a maximum value not only at the vertices 2, 4, and 5, 1, but it has a maximum value of 12 at any point on the line segment connecting these two vertices. So you'll see that. So you'll say the max value is on the line segment of 2, 4, and 5, 1. Okay, so that's how you would notate that, and you will see that again in your homework. The last thing we're going to do is look at an unbounded region. So we'll do an example of an unbounded region and what that looks like. So some linear program problems have no optimal solution. This can occur when the region determined by the constraints is unbounded. So here is an example of that. So we have the maximum value, find the maximum value of z equals 4x plus 2y with our objective function there. And then x is greater than or equal to 0, y is greater than or equal to 0, subject to the following constraints. So again, with the rules, we have to graph these, graph all of our constraints, shade it, and then find our answers after we plug in the vertices. So let's do that here. So let's graph. We have x plus 2y is greater than or equal to 4. So let's rewrite this. 2y is greater than or equal to negative x plus 4. Divide by 2. So we get y is greater than or equal to negative a half x plus 2. So at 2, and then down 1, right 2, down 1, right 2. And so here is my graph. And then it says greater than, so I know that I'm going to shade to the right of this. Then let's look at the other equation here. So y is greater than or equal to negative 3x plus 7. The slope is negative 3. So nice, it hits that spot right there. And then it's greater than, so we know we're going to shade to the right of that. Then the last equation, we have 2y is less than or equal to x plus 7 divided by 2. So y is less than or equal to 1/2 x plus 7 halves. So that is 3.5. Here, down 1, right 2. It's up 1, right 2. Up 1, right 2, up 1, right 2. So it's doing this here. And then it is less than, so I'm going to shade below that line. So in here. So therefore my solution region, I will shade it all in, will be here. So notice that it is unbounded. It's going forever. It's not enclosed like our previous examples. So let's label our vertices, which we can read fast. 1, 4. And then this one is at 2, 1. And then another one here at 4, 0. And then, of course, we have our constraints here. Y has to be greater than or equal to 0. X has to be greater than or equal to 0. So here are our vertices. In this case, we're asked to find the maximum value. We actually can't find our maximum value, but in the homework, it's going to ask you to find the maximum and the minimum value. So you would find the minimum value, whatever that is. You plug in the vertices, but then for the maximum value, you could write no max value, unbounded. Unbounded. But you could find a minimum value, right? So it's one of these 3 points here. Now here, this is asking for finding the minimum value. So go ahead and try this example here. Okay, so trying this out, you should have gotten this graph. So I figured out the x and y intercepts for my first one. The purple line is 0, 8, and 8, 0. And then the pink line here, I graphed it. The y-intercept is 6, and I used a slope of -3/5. Then I identified my vertices. I shaded everything. And then I plugged in each of these vertices into my objective function. Then the minimum value is asking for the minimum value, and so that is the smallest number, and that is 30 when I plugged it in here. So minimum value of 30 when x is 10 and y is 0. And then there is no maximum value because it's unbounded.